For our last lesson in this chapter, we're going to look at all the different types of graphs that we've talked about so far this year. In one chapter, we learned about linears. That's when we make a line. In another chapter, we learned about exponentials. That was the curve. And then in this chapter, we had our parabola, which was quadratic. So we're going to look at linear, exponential, and quadratic functions and look at how you determine whether a function is linear, quadratic, or exponential. One way that you can do it is to just plot points very easily and see what happens to the graph. So I just want you to pause. I want you to plot A and B and C and look up at the pictures and say what type they are. Really straightforward in example 1. Please pause now. There's letter A. There's letter B. And there's letter C. Don't forget to make that little tail over here, which we called the asymptote, which would be 0, I'm pretty sure. But we don't know the equation, so that's just my guess. Another thing that you can do, rather than just graphing the points, because that can be time consuming, is use patterns between consecutive numbers in the table. Now, we didn't call it this, but the difference of consecutive y values are called first differences. And the difference of those differences is called second differences. And then you say to yourself, why do I care? Well, we know that linear functions have constant first differences, right? Constant addition or subtraction. In exponentials, we know that the y values have a common ratio, which we call the multiplication or division relationship. When you're talking quadratic, the second differences are constant. So that's why we need to know about second differences, because it helps us to determine if something is quadratic without having to graph it. In any case, the x values have to have a constant relationship, a constant pattern, but if it doesn't, then it's not worth looking into, or you might have to graph it. So let's look at what makes a table linear, quadratic, or exponential. In letter A, first, we look at the x values and we make sure that they're constant. And in all the cases, the x values have a constant pattern. So now I can look at the y's. So now let's do that. So in letter A, this is minus 3. This is minus 3. So you can see it went down by 3 every time. Since it's a constant subtraction, letter A is linear. Now let's look at letter B. In letter B, it's a constant multiplication by 2, right? Times 2, right? So you see the pattern would continue. So letter B is exponential. Letter C is probably quadratic because that's what we're looking at today. And let's look at what happens. So when we look at our pattern, we see that this is minus 1. That's plus 1, and you're like, huh? But keep going. That's plus 3, and that's plus 5. So that's the first level of differences. Now let's do the differences of those differences. So to go from negative 1 to plus 1, it's plus 2. To go from plus 1 to plus 3, it's also plus 2. And to go from plus 3 to plus 5, wow, it's also plus 2. So you can see that the second level of differences is constant, which makes letter C quadratic. Okay, let's look at an example of when we have to determine what type of function it is, and then we're going to write the equation for the function. So just as a side note, this really doesn't have anything to do with example 3 right now, but linears are the form y equals mx plus b. Remember, m is the slope and b is the y-intercept. You might want to write this down. Exponentials were y equals ab to the x, where a was the y-intercept and b was the common ratio. And then in our beginner level of quadratics, we saw y equals ax squared, and we know that it can get more complicated, but that's as far as we're going to get for writing our own. No, A just stands for the number that you multiply by to make it narrower or wider. So there isn't a super easy way to figure it out. We have to just kind of plug our values in. So first we have to determine if it's linear, quadratic, or exponential. And we could do the second differences, and we actually are. But easier than that, you can see the symmetry. You see the x values have a constant pattern, and you see the symmetry in the y values. So that's a dead giveaway that it's going to be quadratic. But let me show you the second differences trick as well. So this would be minus 12 minus 4 plus 4 plus 12. So now the second difference is negative 12 to negative 4 is plus 8, negative 4 to positive 4 is plus 8, and 4 to 12 is plus 8. So that's another way to confirm that it is quadratic. Anyway, so we've now identified that it's quadratic. Great, now what? There's no easy way to identify what the a value is. So what you do is you take your equation and you plug in a value from the table. So y equals ax squared. And I'll just pick, I don't know, like whatever. I'll pick this one. Don't pick any ones with zeros because that just kind of like makes all the numbers disappear. Even though I usually tell you 0 is easy, 0 actually makes it harder. So 12 equals a, because I don't know what it is, times 2 squared. So I can easily do that. That is 3. So the equation for this would be y equals 3x squared. If it were shifted horizontally or vertically, it wouldn't have been able to get done this way, but we're going to keep it beginner level. Something that you can do with nonlinear graphs is look at the rate of change. Now we know rate of change is another word for slope. So linear functions, right, graphs that make lines have a constant rate of change. Nonlinear functions do not. So what we can do is we can compare functions and see which one is increasing or decreasing faster using their slopes. So we'll call that their average rate of change. The average rate of change of a function between 2 points is the slope of the line connecting those 2 points. So for example, if we look at this green line, the slope of this green line, it's comparing the rate of change between these 2 points. It's steeper than the rate of change between these 2 points. So we would say that this exponential function has a greater rate of change between these 2 points than does the quadratic function. Down in example 4, we've got 2 social media websites that are open their memberships, and they want us to compare the websites by calculating these 2 intervals. They want us to look at how they compare from day 10 to day 20. So what we're going to do is we're going to find the slope here, and then we're going to find the slope. Go with me to website B. We're going to find the slope between these 2 points, and then see which one is bigger. So the table website A is obviously going to be easier for me because it's already written out in points. So it would be 2150 minus 1400 over 20 minus 10. So that would be 750 over 10. So that's 75 as its slope. And then this one, let me estimate. So it's probably like 780, that's my guess, and 20 would be 1800. So let's find the slope there. It's going to be 1800 minus 780 over 20 minus 10. So that's 1020. Over 10, so it's 102. So then a website B is faster. It doesn't necessarily mean that website B is always faster. It just means from day 10 to 20, website B was faster. The last thing to do is letter B, predict which website will have more members after 50 days. Well, at 25 days, the memberships are pretty equal. This has 25, and this has, what is that? That's about I want to say like 2400 because it looks like it's going, 6, 12, 18, 24. So they're pretty much the same. This one's a little bit more, but that's at day 25. We want to go to day 50, and we know from exponentials that exponentials grow way faster. So website B is going to have more members because at that point, website B is now going to surpass website A. I wrote website B will be greater because it passes website A around 25 days. If you wanted to explain about the linear and exponential, you could have done that. I want to save this example for class because at one point we're going to need to use a graphing calculator to solve one of the questions. So let's hold off on that, and if you have any questions, write them down and ask me when you come to class.